So hello students, so we are discussing about the module 4, which is on embedded system design concepts. So basically we know that when we want to design a particular embedded system, we need to follow some particular steps, right? Or we should know this particular things initially when we are starting to build any particular embedded system. So that's what we are discussing. So initially we are discuss about the characteristics and quality attributes of an embedded system. Then we are discuss about the operational quality attributes, non-operational quality attributes, embedded system, whether it is application specific or domain specific, and hardware and software co-design and program modeling. Okay, so we know that whenever we want to design an embedded system, we need to follow particular steps. So if we know these things previously, it will help us to design that particular embedded system in a better way, right? So we have to first document what is the characteristics we are looking for in our embedded system, what are the quality attributes we are looking for our embedded system, whether it will be application specific or domain specific, what are the hardware requirements, what are the software requirements are required, which part we are gonna design with using only hardware, which part we are design only software, right? That things we are discuss. And in the last class we are discuss about the program modeling also. So which particular model we will be using to represent our our embedded system, right? So like a data flow graph model, control data flow graph model, or state machine model, or sequential model. So all that we are discussing in the last class. So we know that once the model is ready, now we can easily write a particular firmware for that particular embedded system. So the last topic what we have is embedded firmware design and development. Okay, so now we need to write a firmware for our particular embedded system. So embedded firmware is responsible for controlling the various peripherals of an embedded hardware. Okay, firmware is considered as a master brain of an embedded system. So whatever the code we are writing, according to that particular embedded system is gonna operate. Whatever the peripherals we are connected with that are gonna operate. So we know that we are doing in a lab some experiments, like, so we are controlling a DC motor to rotate in a clockwise anti-clockwise direction. So that is nothing but we are doing it by writing a code in it. So in the code we are mentioning whether to write clockwise anti-clockwise, and according to that it is operating, right? So the same, so whatever the embedded system need to operate, that code we are writing into it. So that is the intelligence. Okay. So imparting the intelligence to an embedded system is one time process, and it can happen at any stage. It can be immediately after the fabrication of the embedded hardware or later stage. So we need to dump that particular code into that particular hardware. Okay, so that can be done at any particular stage. Once the intelligence is imparted to that embedded product, by embedding the firmware in the hardware, the product start functioning properly and will continue serving the assigned task till the hardware breakdown occurs or a corruption in the embedded firmware occurs. So once you are dumped this particular code into it, that particular embedded system will start working. But sometimes if the hardware breakdown occurs or any particular corruption is occurred in software, then it will stop operating, right? Designing the embedded firmware requires understanding of the particular embedded product hardware, like various components interfacing, memory map details, IO port details, configuration of the register of various hardware chips, and some programming languages. So basically these all things, if we are knowing properly, then only we can easily write the code or the firmware for that particular embedded system. Okay, like a hardware, which microcontroller we are using, what are the pins we will be using to connect the external things to that particular microcontroller, or what are the configuration registers are required to configure. So all these things, if we are knowing properly, then only we can write, or if the basic language we are knowing, then only we can write a firmware for that particular embedded system, right? Like we can take an example what we are doing in a lab. Simply we are writing a code for a stepper motor, right? So first we need to know that which microcontroller we are using and what pins of that particular microcontroller we are connecting the stepper motor, right? and what registers need to be configured of that microcontroller to access that particular pins, right? So if that is knowing, then only we are able to write a code for that particular embedded system or that particular task. Yes or no? So that is what, if we know all this, then only we can easily write a firmware for that. So embedded firmware development process starts with the conversion of the firmware requirement into a program model using modeling tools like unified modeling language or flowchart based representation. So we can start working on a firmware once the model is ready, as we discussed in the previous class. So if it is having a particular model or a flowchart is ready, then we can easily write a firmware for that. Okay. The firmware design approach for the embedded product is purely dependent on the complexity of the function to be performed and the speed of operation is required. So what code or the firmware we are writing is depend on the complexity of that particular function and the speed required. So these are the two main parameters we need to take when we are writing the firmware for that. What approach we will be using to write that particular firmware. Okay, two basic approaches are there. So the first one is a conventional procedural based firmware design, and the another one is embedded operating system based design. So these are the two approaches we can go for. So the first approach is nothing but also called as a super loop model. So the conventional one also called as a super loop model. So let's discuss that particular approach. The super loop based approach. The super loop based firmware development approach is adopted for applications that are not time critical and where the response time is not so important. Okay, so this kind of approach will be used where the applications are not time critical. Okay, the response time is not so important. So we know that we have already discussed this kind of particular examples, right? So that kind of applications we will go for a super loop based approach. Okay, it is very similar to a conventional procedural programming where the code is executed task by task. Okay, so it is written task by task in a code and that will get executed. The task listed at the top of the program will get executed first, and the one which is listed at the last will get executed at the last. So here you can see that the firmware execution flow, how if we are writing a super loop, how the execution flow will be there. So first is configuration. So configure the common parameters and perform initialization for various hardware components, memory, registers. So first is configuration and initialization. Then start first task to be executed, then execute the second task, then next task, continue till the last task, and once the last task is over, again jump back to the first task. Okay, so that's how it will happen. So simple example, we are discuss about a stepper motor, right? Or you can take an example of a DC motor, anyone. So first task is what, configure that particular which pins are connected for which pins are we are using of a microcontroller to connect our DC motor. Okay, which registers we need to configure. So all that is initialization and configuration. Once that is done, what is the first task? Rotate the motor in a clockwise direction. Stop the motor is the next task. Then rotate it in an anti-clockwise direction. Stop the motor. That is the fourth task. Like that we are written, right? And once that is done, again jump back to the first task, rotate in a clockwise, anti-clockwise. That is what continuously it will happen. So task by task, whatever we have written that particular program. Okay. From the firmware execution sequence, it is obvious that the order in which the tasks to be executed are fixed and they are hard coded in the code itself. So which task has to go first, which task has to go next, that's what we have already written properly in a code, and that according to that only it is going to execute. Okay, so in a simple C language, if we are writing that particular thing, how it will be, so initially main, then configuration and initialization. Okay, then while 1, then task 1, task 2, task 3 up to task n, and again it will go back to task 1. So this is how a super loop can be written, what we are saying. Okay. So almost all the tasks in the embedded applications are non-ending and are repeated infinitely through the operations. So not for all embedded system, but many of the embedded system the tasks are non-ending. Like you can take an example of our traffic control system. Okay, so all the traffic lights are continuously sorry are continuously operating day and night, right? So that is what we can say, that never ending, it will continue. Okay, so that is what we are saying. This can be like, there we are using like a super loop, so where while one and continuously that task are gonna run. From the above C code, you can see that the task 1 to n are performed one after the another, and when the last task n task is executed, the firmware execution is again redirected to the task 1. Okay, so that is what is a forever loop we are saying. Okay, this representation is achieved by using an infinite loop, hence we are written as a while one, so it is always true and it will continuously in that particular loop. So this approach is nothing but referred as a super loop based approach. Okay, since the tasks are running inside an infinite loop, the only way to come out of that loop is either a hardware reset, or if any interrupt is occurring, so then only it will come out of that, right? So that particular traffic control, or you can say that another example as a digital watch, so it will continuously running. Okay, so if you want to stop it, either you have to power off it or hardware reset it, so that only you can do, and it can stop that particular embedded system. Okay, so the super loop based design doesn't require an operating system, since the task scheduling and all is not required, because we know that whatever the task has to be executed first, that we are writing first in this particular loop, and it will go one by one. So there is no OS is required for this super loop one, because we are not assigning the priorities, or we are not scheduling the particular task, because the sequence of execution is already fixed. We are not able to change it. The type of design is deployed in a this type of design is deployed in a low cost embedded product, and the product where the response time is not time critical. Okay, so simple example I can give is like our electronic toys. Okay, where you are pressing some button and it will pronounce that particular thing, like if you press A it will pronounce A, that kind of things, or any gaming things embedded. So there the response time is not that critical. Okay, and this product cost is also less. So now what are the drawbacks of this particular super loop approach? The major drawback of this approach is that any failure in any part of a single task will affect the total system, right? Because one by one task is going to executed. If any one task fails, it will stop there and it will damage the particular all execution. Okay, or if the program gets hangs at particular point, it will be there forever and it will stop functioning of that particular embedded system. What is another major drawback is that in the super loop design approach, the lack of real timeliness. Okay, if the number of tasks to be executed within an application increases, the time at which each task is repeated also increases. Okay, so number of tasks increases, then repetition also increases many times. So if it is running faster, sometimes a particular task will get skipped. Okay, so that skipping of that particular event may occur, so that is also a drawback of this particular super loop approach. Then the next approach is our embedded operating system. Okay, operating system based approach. So where the embedded system task has to be performed or where are so much critical and the response time is also required faster, or where we need scheduling of the task or prioritizing the particular task, there we need this particular operating systems. Okay, so the operating system based approach contains operating system, which can be either a general purpose operating system or a real time operating system. Okay, the general purpose operating system based design is very similar to the conventional PC based application development, where the device contains an operating system. Okay, and you will be creating and running some application on it. So simple, your desktop or PCs where we are having operating system in it and we are running some applications on it, like you are playing some songs or playing some video on it, or playing some games, that are the applications you are running on that particular operating system. Okay, so either that one is there, or the another one is a real-time operating system based design. So is employed in embedded product demanding the real-time response. Okay, our real-time operating system response is timely and predictable manner to the events. A real-time operating system allows flexible scheduling of the system resources like the CPU and memory, and offers some way to communicate between the tasks. So that's what I said. The real-time operating systems where the particular embedded system tasks are very critical and response time is also critical, and where you required multiple tasks are running at the same times, which will require to access a CPU or memory. So that kind of embedded system, we need this approach of real-time operating system. Okay, we know that for like in aircraft control, we need this kind of operating system where many tasks are running at the same times and responding in a time critical manner. Most of the mobile phones are built around the popular RTOS Symbian. Okay, so this is what is an example of a real-time operating system, I can say. Okay,